Let's work on a problem where we have several charges and we're going to apply Coulombs law equation to solve for the force acting on one of these charges. So we have four charges, each one has a charge Q, and they are located at the corners of a square. The side of the square is A, and we're trying to find the net force acting on the charge at the bottom right. So we would like to find that vector, force, net force acting on that charge, magnitude, and also the direction. Since it's a vector, we need to specify both of those quantities. So that's the question. So first thing that we're going to do is label these charges. That's going to be charge number 1 on the upper right, upper left, and bottom right, 1, 2, 3, and 4. So that will be, we're going to use this to label the forces so that it's not so confusing. So we're looking for the net force acting on charge number 4. That net force is going to be the sum of the force that charge number 1 is putting on charge number 2 plus the other forces. But this force, as you can see, 1 on 4 is going to be a repulsive force, and acting on 4 will be a downwards force. So that's our vector F14. We also have charge 2 applying a force to charge 4. Notice that charge 2 is across the diagonal from 4. So that force is going to go along the diagonal. So if you draw the diagonal, the vector F24 should be pointing in that, should be along the diagonal, and of course is pointing away from charge 2. We're looking for the force on charge 4 due to charge 2. 2 is pushing away charge 4. So the force must be pointing in that direction at basically 45 degrees from the horizontal. And we have one more force, which is the force that 3 puts on 4. So notice that 3 is directly to the left of 4. It's a repulsive force because, as you saw in the picture, all the charges are positive. So 3 is pushing 4 away. So the vector force 3, 4 points to the right. All right, so let's start with this force. We're going to write down the magnitude and direction of this force. So as you can see there, well, it is a Coulombic force. It's a force of repulsion between two charged objects. So we need to use Coulomb's law for this, which says the force is the electrostatic constant K times Q1 times Q4, the two charges involved in this interaction, divided by the distance between the charges, which is the same as the side of the square. So that's going to be divided by a squared. And if we want to put in the direction here to specify this vector fully, then we're going to put a minus sign and multiply this whole thing by j hat, because remember that j hat is the unitary vector in the vertical positive direction. So since this force is pointing straight down, we specify that direction with minus j hat. So the force that 1 puts on 4 can be fully expressed as a vector minus kq squared divided by a squared times j hat. All right, moving on to the force 3 on 4. That is a force that goes straight to the right. The magnitude is given by Coulomb's law. Again, the charges are equal to each other. Q3 is the same as Q4. So we get kq squared divided by, the distance between them is again a, and you square that, so divided by a squared. And the force is pointing straight to the right, so that means it follows the direction of I hat. So we just multiply by I hat, and this is the full vector force 3 on 4. That's the distance, we just said that. Now the last vector that we need to add here is this little vector. I drew this vector smaller than the other ones because notice that the distance across the diagonal is longer than along the sides. So charge number 2 is further away from charge number 4. So it produces a smaller force. Everything else being the same, the distance is the dominant factor here. And since the distance is longer than for the other two forces, then it's going to be a smaller force. Let's see, so what magnitude does it have? Coulomb says K, Q1 times Q2 times Q4, but all the charges are equal, so we end up with Q squared. And we're going to divide by the distance squared. What's the distance between those two charges? That distance is square root of 2 times a. See if you can prove that. Think about it for a second. This is the length of the diagonal in a square. So if you draw the side of the square on the left and at the bottom, you notice that that and the diagonal make a right angle triangle. The opposite of this right angle triangle is A, the adjacent is also A, and we're looking for the hypotenuse. That's going to be our distance, D. So what's the hypotenuse if the opposite is A and the adjacent is A? So just write down Pythagoras theorem and you get to the answer that the hypotenuse is the square root of 2 times A. So the diagonal of a square is equal to the square root of 2 times the length of the side of this square. All right, so that's why we got square root of 2 times A in the denominator, and you need to square that according to Coulombs law. And the direction, gotta be careful with the direction. This is a vector that is pointing in that diagonal direction, which is 45 degrees below the x-axis. So the x component of this vector will be the hypotenuse, kq squared divided by square root of 2a to the square. The hypotenuse multiplied by the cosine of 45 degrees. And that will give us, multiplied by I hat, gives us the x component vector of the force. The y component vector, notice that the angle is 45 there. The y component vector is going to be kq squared divided by square root of 2a, all that square, but we need to multiply now by the factor minus sine of 45 degrees times j hat to get the direction correctly. Notice that the cosine of 45 again came from the x component. The minus sine 45 is going to come from the vertical component. We have to multiply the magnitude of the vector times the sine, in this case minus sine of 45, because the angle is 45 below the x-axis. So those are the two components of the vector F24. Remember that when we're dealing with vectors, we have to be careful with adding the vectors as components. If you're adding vectors, you need to break it down into components and add component by component, never mixing the x component with the y components of anything. So we got all the vectors expressed in x and y components with the I hat and j hat vector, unitary vectors, so we can proceed to add them. So the first vector, F14, I'm going to write it up there again on top of the screen, minus kq squared divided by a squared times j hat. The second vector, the F24, we have it as kq squared over, notice that the square root of 2 squared becomes 2, and then in the denominator a squared, and then multiply by cosine of 45. If you remember from your trig classes, cosine of 45 is the square root of 2 divided by 2, so I wrote that times I hat, and then minus sine of 45 is minus square root of 2 divided by 2, and then we multiply by j hat. So that was the vector, that is the vector F24. And finally the vector F34, which we wrote as kq squared divided by a squared times I hat. Now everybody has an I hat and a j hat, so now we're ready to find the final components of, or the final net force, which is the sum of these three vectors. So we put together everything that has an I hat, we're going to put it together, add it together. So that gives us kq squared divided by a squared, that we can factor out of those two terms that have an I hat. So one of the terms is square root of 2 divided by the 2 in front of the parentheses, and the 2 in the denominator of square root of 2 divided by 2 gives us 4. And notice that the second term is just kq squared over a squared, so when we factor it out, we put a 1 for the second term, and that is in the direction I hat. So I've added the terms that have I hat, so that means adding the x components of all the vectors that add up to the net force. Moving on to the y components, so we have these two terms. We have the first one with the j hat, so now we're going to add the j hat terms. So the first one is minus kq squared divided by a squared. So if I'm going to pull out kq squared over a squared out of the parentheses, then we're going to have a parenthesis minus 1 for the first term, and the second term is going to give us a minus square root of 2 divided by 2. But there is another 2 here. Don't forget these 2 here. Oops. Don't forget these 2 here. So these 2 and these 2 are going to become a 4 right there. and then there's the square root of 2 over here, which is square root of 2 over here, and this whole thing goes multiplied by j hat. So I put together the terms that have I hat, together the terms that have j hat. Notice that this term and the two terms are the same, except that one is positive, the other one is negative. Everything is the same. We have the square root of 2 over 4 plus 1, just that in the second term is just negative. So the force is going to have two components that are identical to each other. The x component and the y component are equal in magnitude for our net force. The net force, that means the net force is going to be pointing in the 45 degrees below the positive x direction. What is the magnitude of that force? Well, the magnitude is going to be q squared divided by a squared times the square root of 2. Why the square root of 2? We have the square root of 2. We already talked about this. So we're talking about having the x component is a number, the y component is the same number. So how long is the hypotenuse? So in a right angle triangle with side A and A, the hypotenuse is the square root of 2 times the length of a side. So the magnitude of the net force, since the x component is equal to the y component in magnitude, then the net force, which is the diagonal, is the magnitude of one of the components. So that will be kq squared over a squared times this 1 plus square root of 2 over 4, the magnitude of one of the components, but multiplied by the square root of 2 because of what we just discussed about right angle triangles that have the opposite equals the adjacent. So, sorry about that, let's clean up here. A little too messy. Let me clean this up, just a second. I think I cleaned it up. Okay, so we just put in multiplying square root of 2 and moving it inside the parentheses. So the first term becomes square root of 2. The second term inside the parentheses becomes 2 divided by 4, which is 1/2. Just to do a little bit of algebra to make this look a little better. So if you put in the numbers in your calculator, square root of 2 plus 0.5, 1 over 2, gives you 1.91. So that's our numerical factor, 1.91 kq squared divided by a squared. We just found the magnitude of the net force, the magnitude of that net force acting on that corner. The direction is going to be, in general, to find the direction of a vector, you do inverse tangent of y divided by, inverse tangent of the y component divided by the x component. In this case, we know that both components are identical. It's just this number is equal to that one, but with a minus sign. So the answer is pretty simple. You could put it in your calculator, but that would be wasting time. The angle is going to be 45. So our final answer, we can write it as the net force acting on the charge at the bottom right corner is going to be 1.91 kq squared over a squared, and the angle is going to be 45 degrees south of east, or you could write it as minus 45 degrees as the direction of the vector. All right, that's it for this problem. See you in the next video.